Now that we've looked at the Clausius inequality, we want to move on to a definition of entropy. So entropy is the analytic tool that we're going to be using to make decisions based on the second law. In other words, it's going to give us a way to determine whether processes are possible or not. And that's what we've been talking about all along in our second law discussion. So let's move on to that next. So we know that the integral of a system property over a cycle is 0. So remember, that's one of the characteristics that we identified for system properties. So things like pressure, temperature, internal energy, enthalpy, specific volume, all of those things are properties or system properties or state functions. And one of their characteristics is that if you go around a cycle and return back to the same spot and add up all of the changes in any of those quantities, it comes out to 0. So here we're just reminding ourselves of that fact. The integral of a system property over a cycle is 0. Well, we've just found something that has that characteristic. We just looked at the integral of delta Q over T for a reversible cycle. That was for the Carnot cycle. And we found out that came out to 0. So we're going to do this in reverse. We're going to say we've identified something who follows this characteristic, and so it must be a system property. So we need to give that system property a name, and the name that we give it is entropy. So we identify a small change in this system property as being delta Q over T for a reversible path. So again, the name for this is entropy, and the symbol that we're going to use for it is an uppercase S. And if we look at the right hand side of this definition, we see that the units are going to be joules over Kelvin. Now notice that this is an uppercase Q, therefore this is an uppercase S. There is also specific entropy, which is just the same thing but on a per unit mass basis, and again it'll be a lowercase s following our convention. The name now is specific entropy, and we see in the units that it's on a per unit mass basis. So entropy is a new property, and the notation follows that same convention. Uppercase is the total entropy, lowercase is the specific or the entropy on a per unit mass basis. Now what we really want to do is look at a single process. So far we've looked at entire cycles. We've looked at a Carnot cycle and identified what its efficiency is, but what we need is something that we can use to look at a single process. So that's what we're going to do now. So we want to look at the entropy change for a process, not for an entire cycle. Well, so far we've only looked at entropy in the context of an entire cycle, so we're going to use that to figure out what the entropy change for a process tells us. So here's a process we're going to look at. We're going from state 1 to state 2 along some path, and that path is described here as being irreversible. In other words, there's some irreversibilities on this path. This is a real path or a real process. So something happens and we go from 1 to 2 along an irreversible path. Well, so far we only have the ability to look at cycles, so we're going to turn this into a cycle by going back from 2 to 1 along a reversible path. So our intent here is to study this process, but we're going to temporarily here create a small cycle that is our original process that we wanted to study, and then a reversible process from 2 back to 1. So this is a little cycle from 1 to 2 and then 2 back to 1. Well, here's our definition of entropy so far. A small change in entropy is equal to delta Q over T. Notice lowercase q, therefore lowercase s, for a reversible path. So if we look just at this reversible path, if we integrate from 2 to 1, so we're integrating this from 2 to 1 delta Q over T, because that's a reversible path, we know that's S1 minus S2. So this is the entropy difference between those two ends of that reversible path, and of course it must be the same for the irreversible path because it's a state function. Now we know, because we just looked at the Clausius inequality, that the integral of delta Q over T for this entire cycle has to be less than 0, because at least part of it is irreversible. It has some irreversibilities in it, and those are in the original process from 1 to 2. So we know if we evaluate this around this entire cycle, it's going to come out to something less than 0. That's what we did when we developed the Clausius inequality. We showed that that was true. So let's continue to look at this little cycle. We want to evaluate the integral delta Q over T around the entire cycle. It only consists of 2 processes, so this is just breaking that up into those 2 steps, from 1 to 2, and then from 2 back to 1. And we know that has to be less than 0. So here we've just expanded this integral around the entire cycle into its 2 parts. Now we know that S1 minus S2 is the second part of this. So this part is the entropy change because that part of this cycle is reversible. So we talked about this on the previous slide. So we're just going to take it and substitute it into this expression. And we get this part is still unchanged, and we've replaced this with S1 minus S2. And then just move the S1 minus S2 over to the other side of the inequality. So we get S2 minus S1 must be greater than the integral from 1 to 2 of delta Q over T for that originally irreversible process. So this starts to link the entropy change from one point to another to this integral from the beginning point to the end point of an individual process. So that's true for an irreversible process, as we've designated here. But if we want to make a general statement, we know that S2 minus S1 must be greater than or equal to delta Q over T always. So notice what's happened here. We've changed this from greater than to greater than or equal. So we're allowing the possibility of S2 minus S1 to be equal to this integral, and we've dropped the irreversible subscript on here. So that means this second statement is a general statement. It's true for all processes. So if it happens to be an irreversible process, then this will be greater than delta Q over T. But if it happens to be a reversible process, then S2 minus S1 will equal this integral, as we showed when we looked at the Clausius inequality. So this is a general statement that must be true. And notice it's starting to give us a tool, and that tool is entropy, to look at individual processes. Well, how can we use this? So this is just the same equation over again. Here I'm just showing that in differential form. So this is true for the entire process from 1 to 2, but if we look at a small segment of that process, or of any process, we know that ds has to be greater than or equal to delta Q over T. So this is just the differential form of this equation. Now, what I want to do next is get rid of this inequality. This is confusing and difficult to deal with, and it hides some of the usefulness of this relationship. So we're going to get rid of that inequality by adding another term on the right-hand side. So a new term to the right-hand side. And so we do that here. So notice we still have ds, the change in entropy, on the left-hand side. This is now an equality. So ds equals, first term on the right-hand side is still the same, delta Q over T. But the new term that we've got here is delta sigma. And this delta sigma is the entropy production. And that's a measure of the irreversibility. So sometimes you'll hear this being called the entropy production. Sometimes you'll hear it being called the irreversibilities. Those are really interchangeable terms. So introducing this new variable in here has allowed us to eliminate this inequality and write it as an equality. So notice that this quantity, delta sigma, has to be greater than or equal to 0. Now let's just take a look at that. So if delta sigma is equal to 0, we'll look at that case first. Then of course this is gone, and ds equals delta Q over T. So that is ds equals delta Q over T. So 0 irreversibilities corresponds to the equality portion of this symbol. So that's the reversible case. However, if ds is actually greater than delta Q over T, that means that d sigma must be greater than 0, so that plus this add up to ds. So this delta sigma has to be greater than or equal to 0. So we get rid of the inequality here, but we need to remember as a result, this can never be negative. Otherwise, this original inequality is going to be violated. So want to always remember that the irreversibilities are always greater than or equal to 0. Of course, if they're equal to 0, that's the reversible case. If they're greater than 0, that's a real process or an irreversible process. So let's continue to work with this concept. So if we're going between two states, so this is in differential form, this whole discussion, but if we want to go back to this form of the equation where we're looking at a change from one state to another, then we're just integrating this equation really, and we get S2 minus S1 again on the left hand side. It's an equality now, and integral from 1 to 2 of delta Q over T, and then this becomes sigma. So rather than delta sigma, it's just sigma. And that's the irreversibilities that occur as we go from 1 to 2. If it happens to be 0, reversible process, then we're just back to our original statement. Now, I want to continue to work with this equation and just understand how the left-hand side and the two terms on the right-hand side work together to tell us things about processes we might be looking at. So first of all, realize there's three things that can happen here. If that is 0, then that's a reversible process. So no friction, no sudden expansion, nothing like that whatsoever. So delta sigma or sigma equal to 0 is a reversible process. If delta sigma is greater than 0, then that's a real process or an irreversible process. So that's one where some friction, some sudden expansion, some other source of irreversibility. The third case here is never possible. Okay, so delta sigma or sigma can never be negative. So if we're working with this equation and we find that it is, then either the process we're looking at is impossible or we've made some kind of an error in our calculations. So these characteristics are very important to remember about this quantity. Can never be negative. If it's 0, we're talking about a perfect reversible process, and if it's greater than 0, we're talking about a real process. Now what I want to do next is look at how these two terms combine to tell us something about this. And there's a new term that is very important that will come out of this discussion. That new term is isentropic. We'll see that in a moment. If the entropy of a system increases, now remember what we mean by entropy. We're talking about this property. So if the entropy of the system increases, that means this is positive, right? If S is increasing, then ds is positive. So if the entropy of the system increases, then we want to look at the right-hand side to see how might that happen. What could happen that would cause the entropy of the system to increase? Because we can evaluate the entropy from other properties, see whether it increases. In a case where it does, we want to think about why did it increase? Well, this equation tells us why. Because ds, changes in entropy, can only come about from two things, either heat transfer or irreversibilities. So if ds is positive, it means that heat has been added. In other words, delta Q is greater than 0. So the only way this can be positive is if that is positive and or irreversibilities exist, so delta sigma is greater than 0. So if those two things are both positive, or one of them is 0 and the other is positive, then certainly ds will be positive. However, there's another situation that could give positive ds. This could be negative, because remember our sign convention is still at play here. Delta Q can be positive or negative. Heat added, it's positive. Heat removed from our system, it's negative. So it's possible that this could be negative and this positive and the result positive. So this would just have to be larger than this, and the net effect of these two things can still be positive. So if the entropy of a system increases, then heat has been added, that's positive, and or irreversibilities exist, positive, or heat's removed and irreversibilities exist. And of course this would have to be larger than this to make that positive. So there's lots of different combinations of things that can happen on the right hand side to make this positive. So if we see the entropy of a system increase, it's very important that we remember that there's these two things that can make that happen. And we want to look and see which one it is and understand that they are different. The other case, though, if we see the entropy of a system decreasing, in other words, if ds is negative, so we've evaluated the change in entropy and we see it's a negative number, then we ask ourselves, well, how could that happen? We look to the right hand side of this equation to tell us how that can happen. If the entropy of a system decreased, there is only one way that can happen. Remember, this cannot be negative. That can never be negative. So the irreversibilities cannot cause the entropy of the system to decrease. However, heat transfer can, because this delta Q can be negative if heat is being removed. So this is the only way that the entropy of a system can decrease, is by removing heat from it. There are several ways that the entropy of the system can increase. So understanding this slide and how these two things combine together to give that is very important. Now I want to look at this statement very carefully, because there's three words in this statement that we want to concentrate on, and each of those three words corresponds to one of these three terms in this equation. So let's just read it and make sure we understand that. So therefore, a reversible, the word reversible impacts this directly. It says that's 0. So that's what reversible means, that the irreversibilities are 0. Adiabatic means this is 0. So adiabatic means no heat transfer, so delta Q is 0. So a reversible adiabatic process, in other words, both of these things are 0, is an isentropic process. So here's our new word. Isentropic means constant entropy. In other words, ds is equal to 0. So that statement is saying that if that is 0 and that is 0, this has to be 0. So that's fairly straightforward. We know if both these things are 0, that has to be 0. The tricky part of this, though, is to realize that if a process is described as isentropic, so if I say you have an isentropic process from 1 to 2, give you some properties at both ends, so the entropy at the two ends is the same, so ds is 0, that does not mean that both of these are 0, right? So this statement doesn't work in reverse. So if you say isentropic, you can't immediately conclude that it's reversible and adiabatic, because this could be positive and this equal magnitude but negative, and that would give 0. So an isentropic process is not necessarily reversible and adiabatic. And we can remember that by understanding this equation and how the sign of these terms combine together. So isentropic does not mean reversible and adiabatic. However, reversible and adiabatic means isentropic. Now we can continue to work with that. Notice, if a process is isentropic and adiabatic, that means it's reversible. Likewise, if a process is isentropic and reversible, it must be adiabatic. So we want to keep those three words straight. Reversible is talking about this, adiabatic is talking about this, and isentropic is talking about this. Now the next thing we want to look at is that this new property we've introduced is a very useful coordinate for property diagrams. So we've seen PV diagrams quite a bit in the course. We also talked a bit about TV diagrams. So lots of different thermodynamic processes. It's very useful to show them on property diagrams. And it turns out that entropy is one of the most useful coordinates that we could use on a property diagram. So in order to illustrate this, we want to go back and look at our Carnot cycle again. So this is how we've seen a Carnot cycle so far, is on PV coordinates. So just to review, this is an isothermal process. This is an adiabatic process, then another isothermal process, and finally another adiabatic process. So 2 isothermal processes and 2 adiabatic processes. Now remember, for a Carnot cycle, in addition to that, all 4 of these processes are reversible. So when we look at this same cycle, but we change the coordinates to TS, so here's entropy being used as a coordinate on a property diagram, we see something that looks quite different. And it illustrates why a TS diagram is so useful for certain types of processes. Well, let's take a look at these in turn. Remember that 1 to 2 is a constant temperature process. So 1 to 2 is going to be a horizontal line on a TS diagram. And that's why I chose temperature, to make those processes from 1 to 2, and of course 3 to 4 will also be a horizontal line on the TS diagram, just down at a lower temperature. The other 2 processes, remember, are reversible adiabatic processes. Well, if they're reversible and adiabatic, it means they're isentropic. In other words, the entropy is not changing, so that means they're vertical lines on the TS diagram. So Carnot cycle plotted on a TS diagram is 2 horizontal lines and 2 vertical lines. 1 to 2, 2 to 3, 3 to 4, and 4 to 1 completes the cycle. So again, it's a cycle, so we always have to get back to our original spot because we're plotting as a function of 2 state properties. Now there's another characteristic of a TS diagram that I want to look at. So we want to look at this process first of all, the process from 1 to 2. So remember, that's an isothermal process and it's a reversible process. So when we look at that process from 1 to 2 and go back to what we did when we developed the Clausius inequality, we integrate from 1 to 2 delta Q over T. We know that it's a constant temperature process, so this can come outside, and the temperature that that's happening at is TH, our high reservoir temperature, or our hot reservoir temperature, and the integral from 1 to 2 of delta Q is just Q from 1 to 2. So this is really just a portion of what we did when we looked at the Clausius inequality. When we did that, we looked at all 4 processes in the cycle. Here I just want to look at that one process from 1 to 2. So that is equal to this because it's a constant temperature process. Now also, when we defined entropy, we said that for a reversible process, S2 minus S1 is also the integral from 1 to 2 of delta Q over T. That's how entropy was defined. So this tells us that Q from 1 to 2 is equal to TH times S2 minus S1. Notice what we're doing here is just equating this with this because they're both equal to the same thing. So that set equal to this, TH multiplied by both sides. So the heat transfer from 1 to 2 is equal to TH times S2 minus S1. Well, notice that's just the area under the curve on the TS diagram. So we go back and look at this. TH is the height of this rectangle, and S2 minus S1 is the width of this rectangle. So that heat transfer that we've calculated there is the area underneath this line. And notice it'll be positive because S2 is bigger than S1, so S2 minus S1 is a positive number times TH, which is also positive. So the area under the curve on a TS diagram is heat transfer. Remember, the area under the curve on a PV diagram is work. So it has that same characteristic that the area under the curve tells us something. In this case, it tells us the heat transfer. Notice if we were to do the same thing for the process from 3 to 4, we would get the same result. Only now we're down at a lower temperature, Tc, and this would come out negative because S3 is bigger than S4. And the Q from 3 to 4 is negative because heat is being removed. So again, the area under the curve is heat transfer. And remember, the other 2 processes are vertical lines. So the area under them is 0, and those are adiabatic processes. So this works for all 4 processes. It just turns out that for 2 of them, the heat transfer is 0. So the area inside of this loop, or inside of this cycle, is equal to the net heat transfer, which is equal to the net work. So it turns out that the area inside both the PV diagram and the TS diagram is the same, and they're both equal to the net work or the net heat transfer for the cycle. So if we go back to them, that means this area equals this area. So the net area is equal to the net work here, which is equal to the net heat transfer here. And if you take a look at the units of these four things, PV and TS, you'll find that the product of P and V has the right units, units of energy, which are the same as work and heat transfer, and the product of T and S also has the correct units. So the area under each individual process is work here and the heat transfer here, and the net work has to be the same number because Q net equals W net. The next thing to look at here is entropy balances. Now in the course so far, we've looked at conservation of mass and we've looked at conservation of energy. So those are two conservation equations that we have in our toolbox that we can apply to a variety of problems. Well, what we're doing here is adding a third equation to that set. We don't call these conservation equations because entropy is not strictly conserved. Notice we have an entropy production term showing up in our equations that we've discussed. So we don't call them conservation equations, but they really play exactly the same role as the conservation equations. So we can think of them as the third set of equations in our overall conservation laws. So we want to look at this for both closed and open systems. So these are called entropy balances. Well, for a closed system, it turns out we've already been talking about this equation. I just didn't give it the name. So if we look at a closed, trapped, fixed mass, then its entropy change is equal to the integral from 1 to 2 of delta Q over T plus sigma. So here we're just going to review the names that go along with these three things. We've talked about this equation quite extensively so far. So the left-hand side is the entropy change, because it's the change in that property called entropy. On the right-hand side we have the entropy transfer. So this is a change in entropy that is resulting from heat transfer. And again, remember that can have either sign, positive or negative, or of course, if it's an adiabatic process, that's 0. And then the last term here, sigma, is the entropy production, or the irreversibilities. So the entropy change that a system undergoes is equal to the entropy transfer connected to heat transfer and the entropy production. So that's our entropy balance for a closed system or for a fixed mass that we're examining. Now, just like there was an energy equation that had to be modified because there was material entering and leaving our control volume, the same thing happens with the entropy balance. So we're going to just review that equation now. Now, the terms in this equation align with the closed system entropy balance in the same way as the open system energy equation aligns with the closed system energy equation. There's just two big differences. The open system version of both of these equations are rate equations, and I'll talk about that in a moment. And the second thing, of course, is the open system version needs to account for material entering and leaving the control volume. So we'll just review, first of all, the terms in here that align with the closed system version. Well, first of all, the left-hand side, instead of it being just S2 minus S1, it's a rate of change of entropy. So that's where we see that this is a rate equation, whereas the closed system dealt with an amount or a change in some property. So the left-hand side here, we have ds dt, and this S is the total entropy in the control volume. Notice it's an uppercase S, not an S per unit mass. Now, for a steady problem, this is 0 in the same way that that corresponding term in conservation of mass or conservation of energy is 0. So that's called the entropy change, or more exactly it would be the rate of entropy change. The first term on the right-hand side again is entropy transfer. So this plays the role of the delta Q over T term in our closed system. If there is some heat transfer with the surroundings, then that can give rise, or that's one of the things that can give rise to the entropy changing. Now notice here we have a summation over an index J. Well, that just allows for there to be heat transfer between our system and our surroundings at several different places. So we could imagine a control volume that encloses several components, perhaps 2 or 3 different types of heat exchangers, and each of them would be exchanging heat with the surroundings. So each of them would have a Q dot term, and each of them might be doing that at a different temperature. So we would have a different temperature in the denominator. So that is what the summation sign is here for, is for situations where there are multiple places inside of our control volume that are exchanging heat with the surroundings. So remember, this is a control volume entropy balance. So before we apply this equation, we would be identifying our control volume, and there are cases where it will have more than one component exchanging heat with the surroundings. The last term in this equation is the entropy production, and notice it's sigma again. The only difference is it has a dot on top. This is now a rate of entropy production, just like all of the other terms are rate terms. So those 3 terms correspond directly to what we saw for a closed system. The thing we need to add for an open system is the entropy transport term. So each of these is the product of a mass flow rate times the specific entropy at that inlet or the exit. And again, inlets are positive and exits are negative, the same as they are in the energy equation and in the conservation of mass equation. So those are the 2 terms that need to be added to make this equation valid for an open system where there's entropy being transported in and out of the control volume. So this is our control volume entropy balance.